Alright, okay. So in this video, I'm going to be showing you how to stop your large language model from hallucinating using a method called RAG. Hello everyone, my name is Dr. Roderick Tabalba. I'm an AI research engineer working at Research Cyber Infrastructure, and in this video, I'm going to be showing you how to stop your large language model from hallucinating. So RAG stands for Retrieval Augmented Generation. It's a method that combines large language models with the retrieval system so the language model can look up information before it generates an answer. In essence, this is helpful because it allows the language model to be grounded in some contextual information before it actually generates an answer. So RAG has three different components. You have your indexer, you have your retriever, and you have your generator. So your indexer is actually preparing your data to be searched. It's turning these documents into a numerical representation that can later be retrieved by the retrieval system. And there's many ways you can prepare your data. You can set a token limit for the number of tokens to chunk your data in. You can also chunk your data by the number of sentences. So another thing you can have is an overlap. And this overlap number basically tells you how much tokens or chunks you want your indexer to be overlapped with other chunks. The next component in a RAG system is called a retriever. So your retriever is how your system is going to be fetching those documents from that database that you define. And the way that you can define a retriever is you can have something that's called a dense retriever, you can have sparse retriever, or you can have a basic keyword retriever. So there's many different ways you can define your retriever. And the last step in the pipeline is called a generator. So this generator basically just grabs the information that it got from the retriever, and then it produces the answer for the user. So for the generation phase, there's also many different ways you could combine techniques from state-of-the-art research to better improve the answer that the language model is going to give. So the reason why this is useful is this. Imagine you have a large number of data, and then you send this data to the language model and tell it to produce an answer. And say your data had a lot of numbers in them. When you ask the language model to give you an answer based on the documents that you gave it, it's more likely to hallucinate or make up some numbers. And it isn't described so concretely in the research on why this is happening. One of the things that people have studied is actually how much content you are giving your language model. So if you're giving your language model too much data, it has a tendency to degrade its performance on the content that it's generating. So next we're going to jump into a Jupyter Notebook, and I'm going to be walking you through the basic components of RAG and building it from scratch. So now I'm going to be walking you through a Jupyter Notebook that I made for a workshop that I hosted a couple weeks ago. So for this Jupyter Notebook, the first thing I did was press the Run All button, just to save some time so you don't need to see me struggling on pressing Run on all of these Jupyter Notebook cells. So the first cell here, we're loading up a few libraries, and I have some embedding models and a small language model that we're going to be using for our experiments today, for our demonstration. So the first thing you need to know that's not super important, but it's also useful to understanding what are embeddings, is called tokenization. So tokenization is basically how you would break up your documents into smaller subunits. So imagine you have a large document that is 1,000 words long or 1,000 tokens. You can break up that document into smaller subunits. So you can have character tokens, you could have word tokens, you can even have sentence tokens. So GPT uses a special algorithm called byte pair encodings. If you click on this link, so if you click on that link, it'll bring you to this web page where you can learn more about byte pair encodings. This is actually a good website because it goes through the algorithm step by step. I'm not going to go over the algorithm in this video today, but if you want to learn more about it, or if you want me to explain it, you can leave a comment down below and I can make a new video about it. Okay, so back to our Jupyter Notebook. So now that we know what tokens are, next we're going to move into text embeddings. So text embedding is basically a numerical representation of your documents. It's the process of turning text into numbers so the computer can understand it. And just a quick breakdown of how embeddings work. It goes through this process of learning the meaning of words. So words like king and banana have very unrelated meanings. So they'll be placed far apart in this embedding space. Their numbers will be very far apart. Whereas if you had words that are very close in meaning, like king and queen, they would be very close together in this numerical representation. And since these words are represented as numerical representations, you can actually perform some mathematical operations on them, and sometimes it'll give you some really cool results. So, for example, if you have the numerical representations of these different words, like king, man, woman, and queen, if you subtract the numerical representation of man from king, and you add in woman, it'll give you queen. So that's just a cool fact that I learned when I started learning about text embedders. So now you know what tokens are, and now you know what embeddings are. Now I'm going to show you how you can find the similarity between embeddings once they're transformed into this numerical representation. So in this notebook cell, I have an array that has two sentences. Sentence 1 is what is the capital of China. Sentence 2 is explain gravity. And I have some context, which is the capital of China is Beijing, and the gravity is a force that attracts two bodies, blah, blah, blah. So the first thing that we need to do is split up these documents into individual sentences. And that's what this line of code is doing here. So now I have an array of size 2 of this context. In this next code cell, this is the point where you would load in your embedding model, and you would call the encode function to turn these sentences into numerical representations. So I called the encode function on queries and documents, and now we're going to compute something that's called the cosine similarity. So cosine similarity is just finding the angle between those two words in the embedding space, and you're going to call the cosine function on that angle. And that gives you the similarity of how close or far apart those two numbers are. So if you look at the example here, we have what is the capital of China. We can see how close it is to this first sentence in the context. So it has a larger number, which means that it's very similar to each other. Whereas the second sentence that talks about gravity has a low similarity score, and vice versa. The explain gravity sentence is closer to the second sentence that talks about gravity. So for the purposes of this Jupyter Notebook, we needed some information to test the RAG system with. So I went to this website, which just has some text on it. It has some information about Moby Dick, the story, and this code is just basically grabbing the text from that website and stripping out the HTML content. And this is the text here. So one of the things that you need to keep in mind is pre-processing. So some data might include information in there or artifacts that are confusing for the language model to understand. So if you ever have tables, images, or HTML, garbled characters, or lists, you need to define your own way of pre-processing your data in order to remove those artifacts. So I've done this quite a lot in my job on pre-processing data, and I just curated a short list here of tools that I found to be really helpful. So Camelot and Marker are two libraries that are good at parsing tables. Camelot I found to be better to parse tables that are in HTML or PDFs, and I found Marker to be really good at parsing tables off of research papers. And the next two tools here, I have PDF Miner and PyMu PDF, which are two, in my experience, two good PDF parsers. So these PDF parsers work really good on modern PDFs where they also don't have any images. If you use these PDF parsers on older PDFs or even scanned documents, it might have difficulties on parsing that data. So another two tools that was useful is Beautiful Soup and Scrapey, which are two HTML scrapers. Okay, so now we're going to get into the naive implementation of a retrieval augmented generation system. So this is the most basic way that you could construct your own system that does retrieval augmented generation. So the first question that you're going to be asking yourself is, how do I chunk my data and store it in a database? So one of the things that you can do is just define a character chunk size. In this example, I picked a chunk size of 200, and the text that I retrieved earlier about Moby Dick, this is just a list comprehension of grabbing or splitting up that text into a chunk size of 200, and then I'm printing it to and then I'm going to print those results for verification. So here, as we can see, we have chunk 1, and I have chunk 2, and then chunk 3, and so on. So one of the things that you have to keep in mind when you are indexing your documents is that if you define a random chunk size, just say 200 like I did here, you're going to have the problem into splitting up your sentences right in the middle or even cutting off different words. And this isn't optimal for language models because you're not able to preserve the entire meaning of the sentence. So actually, a better way of doing this could be to use a sentence tokenizer, where you can split up your document by sentences. That way you're able to preserve the entire meaning of your documents. But that may not always be the case. And you may need to split up your documents into wide range of different ways to meet your use cases. But for simplicity, we're going to be using this chunk size and for this demonstration. So now that we have an indexer, we're going to move on to how we're going to retrieve those documents from the database. So I just have some queries here. These were generated from ChatGPT. For now, we're just going to test out this first query. What physical impairment did Perth have and how did it occur? So same like earlier in this Jupyter Notebook, the way that we would try to find the similar chunks for this query is that we would first encode the chunks. We will get the numerical representation of the chunks. Then we will do the same thing for the query. And then we would do a semantic similarity between all the chunks that we have in the database and the user's query. And we're going to print the similarity score. And in these two examples, I am printing the chunk that has the highest similarity, and I'm going to be printing the chunk that has the lowest similarity. So here is my tensor, which has all the different chunks in an array, and these numbers represent how similar the query is to each of these chunks. And if we look at the chunk that has the highest similarity score, which has a score of 0.40, we get this chunk here. If we look closer, we see that this sentence here actually talks about the loss of extremities of both feet, which could be the answer to our question. And the chunk that has the lowest similarity score of 0.14 was this sentence. So now we're going to move on to the last step of how to generate that answer for the user. So for this part of the code, I'm not going to get into the details of using the TinyBird language model. Okay, so this part of the code, now that we have retrieved the chunks that may include the answer, or the chunks that are very similar, and then we have the chunk that is not similar, we're going to see how the language model reacts to both different chunks. So here I have some code that uses a Q&A model to try and detect where the answer might be in those chunks according to the query. So in here, we're just going to tokenize the query and the chunks, and then we're going to get the attention, mask, and the input IDs. We're trying to get the portion of where we think the answer might be within the context or within the chunk. We're going to get the start scores and end scores, and then we're going to find so what we're going to do is get the start scores and end scores, and then we're going to find where we think the answer starts within the context and where do we think the answer is going to end, the highest score. And then we're going to turn those tokens back into a string and review its answers. And we're going to do the same thing for the lowest rated chunk that is here. And if we look through the answer, we see that the answer is in the highest rated chunk, the loss of extremities. Answer for the second chunk is altering or repairing, which does not seem like it's the right answer. So the way that we could validate our results is by using a smarter language model. So what I did here was I supplied the text to a smarter language model like ChatGPT, and I gave it the list of questions that I had and told it to answer those questions. So in fact, we see that Perth lost the extremities of both feet was actually the answer of the first question that we had here. Now, if you have access to a language model and you have an API key, this is where you would supply that answer and that query to the language model to produce an answer that's easier for the user to understand. And that's where you would get this code here. So recall, this Jupyter Notebook was made for a workshop that I conducted a couple weeks ago. So what I did was I simplified the code for the user and just defined a generate function to handle all the logic for picking out the answer according to the context. And this is where I introduced a library called ChromaDB. So ChromaDB is just a database on how you would store these numerical representation of your documents. So in this example, in this Jupyter Notebook, we had a somewhat very small text that we had to store in the database. We actually stored it in memory. But if you were to use this in practice, sometimes you might have over 1 million documents that you want to store. And there's no way that you could store this efficiently in memory. So a tool that people would use in order to help with that is called ChromaDB. So ChromaDB is an efficient database that has the ability to store those documents, and when you try to compute something like semantic similarity, it actually has some optimizations in there to assure that it is efficiently comparing your query against all the documents in the database. And then I have some quick code here on how to set up your persistent database. We're just going to define the client and create a ChromaDB within my directory. And then we're going to create a collection. My collection is going to be called my question and answering collection. And then we're going to add those chunks that we had earlier into this collection. And you can store them with some metadata, which in here I'm not utilizing. I'm just naming them the chunk size or the chunks. And you can also assign an ID to them. And then you would apply your chunk embeddings. So in this next section, I'm going to be talking to you about how you evaluate whether your system is performing correctly. So now that you have all these different components defined, say you had a chunk size, you have your retriever, you defined your embedding model, and you're generating some answer. the next question you need to ask yourself is whether the system that you just created, is it performing correctly or not? So the best case scenario is that you have labeled data. You have data that you can evaluate your system on. For example, if you have frequently and answered question data, which I can show you here, this would be the best case scenario where you have questions and you have answers. So the way that you would evaluate your model is that you would have all of these documents as indexed in this vector database. And then you would have your test questions, which would be these here. You would run these test queries against the documents within your vector database. And then you can see whether it matched up to the correct chunk or not. So that's what this code is showing you here. Say that you have your data from ChatGPT, you had some sort of question, and you have the correct answer from it. You would just run your questions against the model and see if it generated the correct answer. And in here, for example, I had the question, what was Perth doing on the deck and why has his forge not stored in this hold? This was the answer that was generated from ChatGPT. And what we can do is see the answer from the model that we just created and what chunk that we got it from. And depending on what kind of model that you're using to generate the answer, you could use another cosine similarity here to see whether the answer that you're producing is semantically similar to the answer that is correctly labeled in your data set. Or you could do something like an exact match to see whether the words that are being detected as your answer from the generated response is actually within the golden standard of your labeled data set. So another option that you could use to evaluate how well your model is producing an answer is by using something that's called a large language models as a judge. And this is frequently used in the research literature, where they basically have a language model that gets the question and an answer, and it evaluates whether the answer is even relevant to the question, or if it basically answers the question correctly, or if it's accurate, or if it's not. So the first time I hear about this, I was a little bit on the fence on whether I would trust a language model on evaluating my documents, but there's actually a research paper that was released on large language models as a judge. And what they found was that the language model that was evaluating the responses performed at an 80-cent agreement with the human responses, meaning that the responses that the language model was producing to evaluate the work, it was performing almost as good as the humans. So even though it was not perfect, in some situations where we don't have access to the people to evaluate whether our language model is performing correctly or not, sometimes a language model can perform just as good. There's also a library here called TrueLens. So another evaluation method that you can use is from this library called TrueLens, which they have their own method or framework on evaluating large language models. And they have a few different evaluations that they did on their framework. I can also get into this in a feature video. If you would like to hear more about it, you can just leave a comment down below. So the third option on how to evaluate your model is actually to generate your own synthetic data set. And this is used quite frequently in the literature, and they have different methods on creating a synthetic data set. But basically, you would run your chunks through a language model, and you would ask it to generate some questions on the data that you supply it. And then you will go through a second step on the language model producing an answer to those questions it just asked. So now you have a pair of chunks, questions, and an answer. And that is a synthetic data set that you can use for evaluating how well your model can produce an answer based on a question. Okay, so the last way that you can evaluate how well your model is producing an answer is by conducting your own experiments on popular used data sets for question and answering. So here are some popular data sets: Hotpot QA, Natural Questions, Squad, Trivia QA, and you can find more data sets from this website here. Okay, so in this next section of the code, I'm actually going to give the code to you guys for you to experiment with. Recall that we had some text that we extracted from a website about Moby Dick. And then in this section of the code, I have a question and answer document retriever class where you can test out different chunk sizes and see how well your system is producing an answer. And you can also test out different question and answering models here. And I also put out some embedding models so you can see which embedding models are performing correctly or not. And the parameters for this class is you can change the different chunk sizes, you can define overlap and see how that affects the answers to the model. You can change out the embedding model, and in these two parameters here, if you wanted to try and test out different Q&A models, you need to pick the corresponding tokenizer with that model. I believe you can't switch up the different tokenizers to the model. You might run into some issues, but yeah. All right, so that's all I have for this video. If you liked it, you can leave a like. You can comment down below if you liked it, and hit that subscribe button. So I'm going to try and put out new videos hopefully every week. These videos are meant to help future upcoming AI engineers get into AI, but it's also a help for me to try and ingrain some of this information into my own brain so that I'm cemented and I have a strong foundation into whatever I'm going to be doing in the future, which is hopefully going to be in AI. Thanks for watching. See you guys later.